but getting section 8.2 done in the time remaining is going to be a bit of a rush, I think. So the homework says, well, I guess you could just read section 8.2, and then the problems will be assigned on the next homework set. So it feels like kind of a shorter homework set, but we've seen the algebra does kind of run away from us if we're not very careful. So I think 5 problems is still a good amount of work on this one. Any questions then before we start for today? Okay, let's start. So we've defined what we meant by the length of our curve by taking a particular limit of Riemann sums and using the mean value theorem. We get something that looks like this. And for this to work, we have to have a so-called smooth curve. The smooth curve just means that if we take the first derivative, it will exist. And it has to be continuous as well. So if f prime exists and is continuous, then the length of the curve is found by that problem process down there. If it's not a smooth curve, you may still find the length of the curve, but you might have to do some other ad hoc method. So it may not be so nice as that formula there. Then what we did next is we defined a so-called arc length function off a base point A. So if we take a point A on some curve, it could be the end point of the curve, or it could be somewhere in the middle. We have a point A, f at A, and this function here, s of x, will measure the length of the curve up to some place. So say, for example, if x is here, in this situation, we'll get a new point here, xf of x, and this little segment here will be the measurement s of x. So the arc length function just tells us the length of the curve so far if you're at x. If we make x go further, our length will increase. If we make x be to the left of a, we'll still be calculating the length, but it's going to be a negative value. So if you want to interpret it as a length again, just take its absolute value and you'll have the right quantity. Any questions about that function so far? Okay, our goal today then is practice working with it. Then if we feel like it, we'll go to section 8.2. So let's take a look at a particular example that makes us use this. This has 2 parts, and part A says to find the arc length function for the curve y equals sine inverse of x plus the square root of 1 minus x squared. And further instructions has to tell us what the base point is, that point A that's used in the formula for arc length. So we'll say, we'll find the arc length function for the curve there at the point, which is going to be something nice, hopefully, 0, 1. That's very nice. So that's a typical problem that you'll see in the homework. I believe that's the last problem, number 35. So if we try to find this arc length function, I'd start off by writing just s of x is equal to the definite integral. Now the next thing we need to do is decide on the lower bound a. We know by formula the upper limit of integration should be x. So what should the lower limit then be? Yeah, exactly. We want to take whatever the x-coordinate is, and that's going to be our base point. So we're going to go from 0 to whatever the value x happens to be of the square root, the same quantity as before, 1 plus dy. And I really, really want to say dx. It feels like the right thing to do. It's not necessarily wrong, it's just frowned upon. And the trouble is there's already x in the problem. So to avoid a possible conflict or confusion of notation, we should write dt, square it, and dt outside. And this variable t can be anything. You could go for y is probably a bad choice, maybe v if you like, anything at all. Question?
Can we still use the notation y prime?
Y prime here? Yeah, that would be just fine. Yeah. Other questions about that so far? Okay, so we have the formula for the arc length function copied in. We use the correct starting base point of 0. The work is now take y, find its derivative, square it, add 1, take its square root, then find the antiderivative. So it's exactly the same process as before. So let's just work it out bit by bit. Y is sine inverse So we can say I'm going to call it a dx because I'm working off this process. And then when we come back, it'll be converted to dy dt, which is really just a dummy variable that will change. Does that make sense so far? Okay, so let's do dy dx, or y prime if you prefer. That would be first derivative of sine inverse, gives us 1 over the root 1 minus x squared. Then we're going to take and add to it the derivative of the square root. The square roots always follow a specific pattern. The whole entire root will go to the denominator. It will be a 1 minus x squared. 2 goes down below with it. Then we have a chain rule set up where we must multiply into the numerator the derivative of 1 minus x squared. And we get a negative 2x altogether by chain rule. Finally, that's our full derivative. So what we know from experience is before we square this, we probably should simplify it as much as possible. So let's try to simplify this down. So dy dx would be equal to 1 over the root of 1 minus x squared. Then it will become minus x over the root of 1 minus x squared. We could possibly try to square it right now, but we're going to get some really nasty terms. The middle terms still involve square roots and so on. So we might as well just combine everything in this situation to a dy dx equals 1 minus x in the numerator divided by the root of 1 minus x squared. So this particular problem, I think that would be the best time to square everything. I mean, I haven't squared everything on this line, so I don't know what's going to happen, but it seems like it's going to be a mess. So here, if we square it, the result will look like that, and now we have dy dx squared is equal to 1 minus x squared divided by, we squared the square root, so this is just a simply 1 minus x squared that way. So that's what we're looking at so far. Does that look all right to everyone to that step? Awesome. So now let's maybe simplify it even further. Why not? The whole thing could be reduced through factoring. So we could say this is 1 minus x squared divided by 1 plus x times 1 minus x. So after cancellation, this will reduce to 1 minus x divided by 1 plus x. So now we have dy dx squared. We're ready to add 1. Questions so far? Okay, so if we go here, add 1 to that whole thing, eventually I'm going to have to go for a pair, we're running out of space. Dy dx squared, 1 added to it, will give us 1 plus 1 minus x divided by 1 plus x. We eventually have to take the square root of that thing. So the square root of that is not going to be nice with the plus in the middle. I think this would be a good time to convert it to a 1 over 1 and add the fractions. I'll visualize the 1 over 1 as a 1 plus x divided by 1 plus x. Let's go for that right now. Then the whole thing would become 1 plus x plus 1 minus x is just a 2 in the numerator divided by a 1 plus x. So that's about as simple as we can make that be for 1 plus the derivative squared. Any questions about the algebra throughout those steps? Okay, so in this step, we create the least common denominator, add across the numerators, kept the denominator, so that once we go and take this process, the square root of 1 plus the derivative squared, this is what we would be looking at. Now we can split it up as, say, the root of 2, which we can kick outside the integral, divided by the root of 1 plus x. Because the power of that is a 1, this is going to work out for us. If it was a power 2, it'd still work out for us, but now it's a trig substitution potentially. And if it's a power 3, we're forced to do things like trapezoid rule and Simpson's rule. But now we take this quantity back over here on the arc length function. We can say the arc length, s of x, is now the definite integral from 0 to x. This whole quantity becomes a root 2 divided by a root of 1 plus, now it's a variable t, dt, by a change of variables for the integrand. That look all right so far? So now for preparation of actually finding the antiderivative, I probably take out root 2, write the antiderivative from 0 to x. The root of 1 minus t in the denominator, or excuse me, plus t in the denominator, is really 1 plus t in the numerator with the power of negative 1/2 dt. So now we're all set up for antiderivative. The antiderivative is going to be a root 2, I'll leave it some space because we'll need a factor from here. 1 plus t becomes power of positive 1/2. If we divide by the new power, it's a multiplication by 2. And the whole thing is evaluated from 0 to x. And if you kept the variable x throughout, say here, here, and here, it really is okay. It just feels funny to have a variable x for which you put x back inside. So people typically shun that, but it is not necessarily incorrect. Just looks funny. So finally we can say by all this work, copy that down, s of x is going to be equal to 2 root 2 multiplies, insert x into this, and we'll have root 1 plus x. If we throw in 0 inside there, it'd be a minus root of just 1, so minus 1. So that's our function. S of x is 2 root 2 root 1 plus x minus 1. Kind of a mess, but remember it's giving us the length of a curve, so it's a really special situation to actually get to this step on an arc length function. Any questions so far about that computation? Okay, so for the curve, sine inverse plus the root of 1 plus x squared, this will give us the length of the curve depending on the value of x, which will either be a positive quantity or a negative quantity. Let's do that very next, just for a geometric interpretation of what in the world we've done. So this next part, B, says to explain the meaning of the equation that reads s at a half, 0.5, is equal to 0.6357. So the problem already did the evaluation for us. Insert 0.5 or a half into the arc length function here, and you should get about 0.6357 and a little bit of change. Then the problem's asking us to say, what in the world does that even mean that s of 0.5 is 0.6357? I think that's a good question to ask. Let's see what it could mean. Any volunteers for a rundown of this equation? Yeah, sorry.
So it's still the arc length, so it's probably from 0 to that point, and that's the length.
Yeah, exactly. So this tells us the length of the curve, and you could recopy it, but it's in context. It's that curve, sine inverse plus the root of 1 minus x squared, from x equals to 0, the base point, x coordinate, to x equals a half, the input into the arc length function, is 0.6357. So that's the magic of the arc length function. If you can derive one like we have, then you can say the length of any segment of that given curve. So that's kind of neat. Any questions about that so far? Okay, let's add another part to it. Another interesting thing we can do to the arc length function is compute its differential. So the next part says, for part C, compute the differential of S, that arc length function. And you do differentials all the time, but this is a special function, so just as a reminder, if y is equal to f of x, then the differential of y is dy equals f prime of x dx. So we want to do that same process for our arc length function, and guess we could do that for this. I mean, we have the function. We could compute that differential right there if we really would like to. Any questions before we start? Okay, so if we want to compute the differential of the arc length function, we had that s of x is equal to 2 root 2 of root 1 plus x minus 1. So getting the differential of that involves writing that ds would then be equal to, here we're taking the derivative of this full entire function right here. If we take that derivative, we'll pass through the constant 2 root 2 by the constant multiple rule. Then we'll take the derivative of that function. So we have 2 root 2 multiplied by the derivative of the root. We'll send the root to the denominator with a factor of 2. We'll multiply the numerator by the derivative of 1 plus x, but that's just a 1 this time by chain rule. Then we'll we'll subtract the derivative of negative 1, and we get a 0 there. So the result is root 2 divided by the root of 1 plus x. So that's our differential. Oh, and don't forget, differential needs a dx. But that result is maybe kind of surprising in a way. Anyone see what's interesting about the result of the differential down there?
We already have that anyway.
Yeah, we did. It's this right here. So in other words, if you want to calculate the differential, you're really just taking the derivative of this, which annihilates the entire integration process. All you'd be really looking at is the thing inside in the process of taking the differential. So that's what we're really seeing happening in our particular example. So let's do another differential where we do just a fully generic one, where the arc length function doesn't have a particular curve we're looking at. Any questions so far with those three parts? Okay, I think that would be maybe a typical exam problem, maybe a little bit long. So if this was an exam problem, maybe part A is done and you have to do parts B and C. Or possibly you have to do just part A and maybe a part B and so on. Those would be typical questions you would see for arc length type stuff on the second exam. Let's do a little bit more and then we're going to go off to the next section. 8.2 on surface areas. So this next process says, consider s of x equals the definite integral from a to x of the square root of 1 plus dy dt squared dt, where the curve C given by y is equal to f of x is a smooth curve. The curve being smooth just means the first derivative is continuous. And the major reason why we keep harping on the first derivative being continuous is then this quantity inside here would be continuous. Squaring it maintains continuity, as does adding 1 in the root. So the whole integrand becomes a continuous function, provided the curve is smooth. If it's a continuous function in the integrand, then the definite integral would exist. So that's the major reason for always tacking that on. So let's take the differential of that then. The problem says find the differential of s. So if that's our function s, we can write that the differential will be ds equals, the next thing after the differential would be a derivative. Let's write it in Leibniz notation, d dx, that's the derivative of the function, which goes from a to x of the root 1 plus dy dt squared dt. So in there is the entire f prime portion of the differential. Then we have to throw in a dx, which is easy to forget. So dx. And that's our full differential. But we still have to evaluate it. So what would happen to the thing inside the bracket? You can see what that should be when we take the derivative of the particular antiderivative we see there. it's almost a trick question in a certain sense. Say, for example, if this was the definite integral from A to B, then that's just a number. So it could be like, say, 12 for the length of the curve. The derivative of that would have been just 0. But as soon as we insert an x, now this thing is a bona fide function. I mean, in fact, our last differential involved root 2 divided by the root of 1 plus x. So we really have something that varies there. And to actually get its derivative, we have to work with our nice friend from a long time ago, the fundamental theorem of calculus part 1. The fundamental theorem of calculus part 1 is specific to the functions that we're seeing here. The arc length function is just like that function g of x, which is defined in terms of a definite integral, where the upper limit of integration varies. So if you take this as your g, take the derivative of that with respect to x, and you get an f of x. Really the short of it is, if you take the derivative of this type of antiderivative that varies with x, you just get the integrand. And the integrand's variable, which is t at the moment, interchanges back to x. So we can say immediately that this derivative is root 1 plus dy dt squared, and we throw in the dx, or excuse me, that should be variable x now. So that's the differential of the generic arc length function. Any questions about that computation? Okay, that's essentially what we've done before to get this differential. The difference now is this object right here was in fact root 1 plus dy dt squared. It just took a long time to actually calculate all that stuff. So the differential is nice in the sense that if you just want to write out the formula, it would be that. But that now has lots of consequences because this as a formula, ds is the root of 1 plus dy dx squared dx, can be rewritten in many different ways. Sometimes people would distribute in the dx inside the root and get some handy formula that reminds us of Pythagorean's theorem. What I think is really interesting is looking at the arc or the length of a curve. If we look at the length of the curve, which goes from a to b of root 1 plus, here we can go dy dx squared dx. That was our old function from before, our old formula. But if we use the arc length function, we can take that whole definition and say the length of the curve from a to b is equal to, by the integral from a to b of ds. And that's now the entire formula. It's kind of a nice trick. And this is a trick that's used in a lot of stuff. So if you go into calculus 3, if you go into vector calculus, complex variables, all sorts of weird moving around differentials like this is at play. So this is something to kind of get used to, I would say. But any questions so far about our differential of the arc length function? Okay, that really beats 8.1 to death. So now we're going off to 8.2. In 8.2, all we're now doing is finding surface areas of particular types of surfaces. We want to do surface areas of surfaces that are obtained by certain kinds of revolutions, either about the x-axis or about the y-axis. Other surfaces, it'd be nice to have surface area formulas for, but if they don't have some nice rotational properties to generate them, we might have to use methods from calculus 3 to effectively get their areas. So this is like a special case where surface areas are suddenly a very doable problem, much like in calculus 1 where suddenly volumes seem very doable, only if there are special kinds of volumes where they're obtained by certain rotations. So this is our setup. We'll imagine, or we'll let C be a smooth curve, once again, described by the equation y is equal to f of x. This being a smooth curve means the function f has a derivative f prime, which is continuous. And we also have a is less than or equal to x is less than or equal to b. Then we want to rotate the curve about the x-axis. we do that, we're going to generate a surface. So let's just sketch something as a rough sketch to that process. So if my curve looks about like this, call that A, it'll just increase for a while, and we'll call that B. The rotation is going to be about the x-axis, and what we pick up is points that look about like this. This may not be perfect, but about like that. So this is the original curve, f of x. And this is another version of it we get when we take the whole thing and rotate in this kind of way. So our surface is going to look about like that. Does that make sense so far? These are difficult to sketch sometimes. Can folks visualize it? Okay, so there's my curve. If I want to get the surface area now, then the trick is we're just going to partition the interval from A to B into n subintervals of equal width delta x. In other words, we're just copying our same exact approach from last section. The reason that's going to work is, even if our partition of the intervals from A to B had just one interval, so delta x is just B minus A, we would get one line segment. If I rotated this line segment, I would get the top half of a cone. And we definitely have formulas for getting that surface area. So that's the method of our approach. We take straight line segments, we rotate them. Those are just segments of cones from which we have formulas. Then we do the summation of all those approximations. Let the number of subintervals increase off to infinity. We find that the surface area, S, is then given by S equals the definite integral from A to B, because of a rotation, really because of the formula for the area of a cone, we get a 2 pi. We also get something extra. We're going to need some kind of radius that comes from the derivation. The radius depends on the type of rotation we make. Either we rotate about the x-axis or about the y-axis. If it is an x-axis rotation, and we're integrating from A to B, we imagine some x between A and B. That would give us a point way up here, and this point here must rotate all the way around down to there. What's really important about that rotation is this height from there to there. But that would just be the height of the curve f of x. And that's what we think of as the radius about that rotation. So we take 2 pi times a radius. In this problem, we could put in an f of x, or remember that y is f of x. So let's just throw in a y. Then we put in ds, and that is does the job. ds kind of shows up there randomly, but the reason it shows up there is ds is this stuff right here, and this stuff is used in finding the length of the curve. So if I want to do this kind of trick of making straight line